And basically what we're going to do today is we're going to find out if we can do more with the equation of a tangent line. Because so far this semester we have calculated the equation of a tangent line by finding the derivative of a function, and we have done a lot of tangent line problems. But right now we can actually do more with the equation of a tangent line. So right now let me write down the equation of a tangent line to a curve to y of fx at the point x is equal to a. So right now we have this equation, and basically we already have seen that we need to find the y coordinate given by f of a. The slope of the tangent line is given by the derivative at x is equal to a, and then I'm just using the slope point formula. So with this equation we can even do more, and to be able to see why we can do more, let me just draw like any function and its tangent line. So right now we have kind of like this square root function, or it looks more like a logarithm. And right now, if we want to find the equation of a tangent line, let's say at x is equal to a, what we're going to notice is that if we're very close to x is equal to a, over here, the tangent line is giving us like a very good approximation of the function values of this function when x is equal to a. So actually what we can do with the equation of a tangent line is we can approximate the values of this function by using the tangent line. So this tangent line can be used to approximate the value of the function value f of x when x is near x is equal to a. So we can actually do that. We can kind of say that f of x is approximately equal to the equation of the tangent line. And you might be wondering, why do we want to do this? If the function is a polynomial, maybe we can evaluate that polynomial easily. But let's say, if we want to evaluate the logarithm of 2 and the cubic root of 30, or a value like e to the 0.1, I need to remind you that in this course we don't have a calculator. So right now, if you want to approximate these values, what we can do is we can use the fact that we know the value of e of 0, we know the value of the cubic root of 27, and well, with logarithm we have to be a little bit more creative, but even with that we can approximate a value, and then we're just going to use this approximation, and this approximation actually has a name. It is called the linear approximation of f of x at x is equal to a. And the only requirement we're asking is that we want the function to be differentiable. So if you're able to find the derivative at x is equal to a, you're good to go, and then the linear approximation is just the equation of the tangent line. And what we're going to do right now is we're going to see this linear approximation into a specific example, because right now with this graph it looks a little bit abstract. So what we're going to do is we're going to use the linear approximation, find the linear approximation of an exponential function. And right now, since you already have seen the chain rule, we're going to continue practicing the chain rule with an exponential function that has a quadratic exponent. So right now we're going to consider this function f of x is equal to e to the x squared minus 1. And right now the first question is going to be very direct. We're just going to find the linear approximation or linearization of f of x at x is equal to 1. And over here, I'm choosing on purpose the number x is equal to 1, so we get an exact number for e to the 0. Oh, let me just bring this over here. So basically, what we need to do is we need to find the y coordinate. Sometimes, you might be lucky and you might have the point, and then in this case, you don't need to find a f of a. So over here, I'm just going to find f of 1. Over here, we have 1 minus 1. So this is e to the 0. And this is equal to 1. Just remember that with any power function, x to the 0 is equal to 1, except when x is equal to 0. Now we're going to find the derivative to find the function that is going to give me all of the slopes of the different tangent lines. So when we're taking the derivative of an exponential function, we just write down the exponential function, especially with the natural exponential function. If you had another exponential function, you will need to multiply your result by the natural logarithm of this base. And now I need to take the derivative of the exponent. So this derivative is going to be 2 times x. And now, after I find the derivative, I can get the slope. So this slope is going to be f prime of 1. And over here, once again, we have 2 times 1 times e to the 0. So this slope is equal to 2. And then I'm just going to write down the equation of the tangent line. The only thing is you have to remind yourself that the linearization is the same thing as the equation of the tangent line. So you have to get used to these equivalent concepts. So right now we have f of a. You just plug in the values, plus 2 times x minus 1. And right now, one thing that we're saying indirectly is that this exponential function is approximately equal to 1 plus 2 times x minus 1. Obviously, when you get far away from 1, the approximation is going to get worse, and it is not going to be that accurate. But right now we want to test, at least indirectly, very informally, why this approximation is quite good when x is equal to is near 1. So right now what we're going to do is we're going to estimate the value of f of 1.1. Just to remind yourselves, what is f of 1.1? We're actually trying to find e to the 1.21 minus 1. So we're trying to find what is e to the point 21, which is hard to find out without a calculator. But right now you're going to see that even if we don't have a calculator, just by using this linear approximation, we're going to get like a pretty accurate answer. So right now the way I'm going to estimate this value is by using the linear approximation. So I'm just going to evaluate L of 1.1, 1 plus 2, and then when we do 1.1 minus 1, we're going to have 0.1. And right now we have this fairly simple value of 1.2. And right now, if you use your calculator to find out what is the actual value of e to the point 21, obviously, I'm just going to provide you this value, e to the point 21. This is actually approximately equal to 1.2337. So this is actually quite a nice approximation, even though this function is just a line. And this gets to show you that with linear approximations, you can do like some back of the envelope calculations into estimating some values that you really can find out exactly. And I'm going to continue with more examples, and basically, my second example is going to be a motivation into how to use linear approximations for finding approximations for the roots of some numbers. So you can actually use linear approximations to estimate the roots of numbers that are close to numbers with exact roots. That are close to, I need to erase this, close to numbers. This is one advantage of this smart notebook. So what am I going to do? Well, we're going to do this second exercise. And just let me know about the time. Probably, right now I've been doing 15 minutes. Consider the following function, and this is the cubic root of x. And what I'm going to do right now is I'm just going to find the linear approximation of this cubic root function at a is equal to 27. So we're going to find the linear approximation of g of x at a is equal to 27. So once again, we're going to repeat all of the steps. We're going to find the derivative of this function. One thing that we need to remind ourselves is that all of these cubic functions are easier to work with if you work with fractions as for your powers. Yeah, with fractionary powers, you're going to be able to use the power rule. So the derivative of this function, we're just going to lower down the power, 1/3 x, and then the new power function is going to have 1/3 minus 1. So this is going to be minus 2/3. And then I still need to find the y coordinate and the slope. But over here we have also another nice trick. 27 is equal to 3 cubed. And this is going to be very useful to find the cubic roots of 27. So the slope of this function, going to say that g prime of 27 is equal to 1/3, 3/3 to the power of minus 2/3. And when we have these power functions, instead of finding the power of 27 and then the cubic root of 27 squared, which is kind of complicated, the best thing to do is just to multiply these two powers using the properties of power functions. Then you're going to have 1/3 times 3 to the minus 2, because we basically have minus 6 divided by 3. And then 3 to the minus 2 is equal to 1/9. So I already have the slope of this tangent line. Just going to find the y coordinate value. And afterwards we're just going to do the linear approximation. So this y coordinate, this is even simpler to find than the derivative. We can just do this, and then these two functions are inverses with respect to each other, so they are just going to cancel out, and then we're going to have 3. And then finally we are going to get the linear approximation. So the linear approximation is going to be equal to the y coordinate 3 plus the slope of the tangent line, which is equal to 1/27 times x to the minus 3. You can x minus 27, I'm sorry, yeah, because you're doing the approximation at a is equal to 27. Yeah, well, I was able to correct that before one student asked me the question. And you can simplify this expression, but my recommendation is, since you're going to estimate some cubic roots, the easiest thing is to leave the linear approximation in this way. So now what we're going to do is we're going to estimate the value of the square root of 30. The cubic root of 30. So now this is interesting because, I mean, we can use a calculator, but right now, if we only have the linear approximation and we don't have a calculator, what we're going to do is that this linear approximation is giving us an approximation to the cubic root. So what I'm going to do instead is that I'm going to say that the cubic root of 30 is approximately equal to the function value of the linear approximation at x is equal to 30. And over here, even though we have to deal with some fractions, this is a fairly easy operation to do. 30 minus 27 is equal to 3. So we have 3 plus 1 over 27 times 3. Then we're going to have 3 plus 1 over 9. And in decimal form, this number is going to be equal to 3, 1, 1, 1, 1, 1. Or you can just put approximately equal to 3.11. And actually, you know, how good is this approximation? The actual value is equal to, also over there, this value is going to be approximately given to you because it's an irrational number, 3.1072. So it is already quite a good approximation. And over here, you also have the advantage of not only finding very quickly the cubic root of 30, but the cubic root of 32, the cubic root of 26 and 25. And the reason why this linear approximation is so good, it has to do with the slope of this linear approximation. Since this slope is very slow, it has a very small value. Basically, for this cubic function, the approximation is going to be quite accurate. So let's do over here 1, 2, and 3. Yeah, over here it's fine. Oh no, I'm just going to use this axis. Now over here, I'm not going to do a very detailed grid for 10, 20, and 30. For approximately, this cubic function is going to have this graph. So over here, you can see that the tangent line has a very small slope. So no wonder we're able to get like a really good approximation. We might even get a good approximation for the cubic root of 20 or the cubic root of 40. And I think I have 10 more minutes. I think, you know, as I wanted to do the example of the linear approximation of sine, but right now I'm going to spend some time into actually telling you how good are the linear approximations going to be. And basically, yes?
Can I ask a question?
Yeah, sure, Udita.
So I noticed in the first example, you had the function, your linearization underestimated the value, and here we're overestimating the value of the actual cubic root. Is there a reason why this is an overestimate and the last one was an underestimate?
Well, it has to do with the nature of the function. Since this function is going to be concave down, with a concave down function, you're going to overestimate the values with the linear approximation. And now I didn't get to draw the other function, the exponential one, but that exponential function looks approximately equal to this. So over here the function is going to be concave up. And I think I was doing it near x is equal to 1. Right now the scale is going to be a little bit way off. So over here, you know, the linear approximation is below the actual function. So over here, the linear approximation is going to underestimate the value. And I'm glad you're asking that because basically this has to do with the sign of the second derivative. And what I was going to do after this example is to present the accuracy of a linear approximation. I think this function was e to the x squared minus 1. So I'm glad you asked that, and that's an amazing question. And you probably, if you're a student, you should consider applying already to grad school. Yeah, it's a really good question.
Can I ask a question?
Yeah, sure.
So one of your earlier multiplication was calculating value of e to the 0.1.
Yeah.
And what should it do if you want to estimate e to the 0.1?
if we want to estimate what e to the 0.0
0.1.
0.
Yeah, so you wrote that on the
Oh yeah, basically I'm glad you're also asking that. And basically, you know, if you have this question, you have a lot of freedom into choosing which function you want to use as your linear approximation. In my case, I use e to the x squared minus 1, but then I consider x is equal to, I believe, 1.1. Yeah. So this one is going to indirectly give you, I believe it was e to the 0.21. Oh, now no, yeah. You see, probably with this function, this might not be the best way to get e to the 0.1. So probably my best recommendation to estimate e to the 0.1 is to use g of x is equal to e to the x. And then we are going to do the linear approximation near x is equal to 0. And I'm not going to bother all of you with all of these details, but basically over here L of x would be equal to 1 plus x. And then if you want to estimate e to the 0.1, you would just say that this is approximately equal to L to the 0.1. And then you would get 1.1. But obviously, you know, another person can come up with an idea and say that I want to use h of x is equal to e to the 2.x. And you can actually use this function to estimate the value of e to the 0.1. But then over here you have to be careful. The x that you would need to do is you would need to use x as 0.05. And there are, especially, you know, with all of these square root functions, all of these root functions, you have a lot of different points where you can do the linear approximation. So I don't know if this answers your question.
Thank you.
Yeah, wow, tough crowd. But I'm glad, you know, you're asking that. You know, I'm always wishing with the students to really ask those intriguing questions, but what do I do if I want to estimate this value? So, the linear approximation of sine, probably, you know, I'm going to leave it at the end if I have some time. Right now, I really want to do something a little, that is really not in Stewart, or if it's done in Stewart, it's done in a very strange way. And right now we want to see how accurate is the linear approximation, and I'm glad that one of you asked me, well, so when your approximation is overshooting or undershooting the estimation. And basically, what we need to find is we need to find how accurate this approximation is. And basically the way we measure the error is by saying, computing the actual function value minus the value of the linear approximation. Over here I'm computing the absolute value, so probably, you know, I'm not going to be able to tell very clearly where if we're underestimating or overestimating. But if we really want to estimate the error, what we need to do is we need to compute the second derivative and kind of like we also need like the interval for your approximation and an interval for the approximation. So normally, you know, if your approximation is centered around A, you might consider that your interval is kind of like x minus A. So right now, the following theorem is going to give me like a good error bound for the linear approximation. And the only thing we require is that the function has a continuous second derivative. So right now, you know, if the second derivative exists, of f of x exists, and then we can find a number m that is bigger than the absolute value of the second derivative, then we can do the following. And this is actually quite good, and then you're going to see that one way of improving the linear approximations is by considering quadratic approximations, cubic approximations, but we really need to get into the topic of how to estimate the error of a linear approximation. And basically, the error bound, basically the maximum error you're going to have is less or equal to this number m that really depends on the second derivative divided by 2 times x minus a squared. And basically L of x is a linear approximation. And right now you're going to see how useful this result is going to be if you really want to know how bad or good your approximation is going to be. And what I'm going to do right now is I'm even going to do kind of like a toy problem. We're going to consider the linear approximation of cosine. And this linear approximation is a little bit counterintuitive, because when you're thinking about a linear function, you're thinking that the linear equation always needs to have a slope. But if you have a constant function, a constant function can be considered as a linear equation, but with a slope equal to 0. So we're going to find the linear approximation of cosine at a is equal to 0. So once again, we're going to do the same steps. Cosine of 0 is equal to 1. The derivative of cosine is equal to minus sine of x. But now the slope of the tangent line in this case is just equal to 0, but it's only because over here we have a horizontal tangent line. And this linear approximation doesn't appear to be linear, but in reality it's just a line with a 0 slope. And you might think about this is kind of like a very ridiculous approximation. I mean, we're basically saying that cosine of x is approximately equal to 1. Obviously, you know, when you're looking at the graph of the one function and then of cosine, you can clearly see that. And I'm not going to draw the entire cosine function. We're just going to put the y-axis over here, and then the x-axis, pi over 2 minus pi over 2. And I'm not going to continue drawing the rest of cosine, because already over here we can see that the approximation breaks down very quickly. So obviously this is not the best approximation, but still near x is equal to 0, the approximation seems to work. So in reality we can use this result to try to estimate how accurate our linear approximation is going to be. So find the error bound of the linear approximation. And right now we just need to digest this theorem and see all of the details. Basically, we're going to need the size of the interval. Right now we're just going to say that this is equal to x minus 0 squared. We need to find the second derivative. And this is where it gets a little bit tricky. So, okay, the second derivative of minus sine of x is equal to minus cosine of x. So right now, how do we find like a good bound for cosine? The nice thing about any trigonometric function is that the values of sine and cosine are always between minus 1 and 1.
Professor,
Yes?
can you stop here and continue next time?
Okay, so if time's up, let me just finish and write down the error bound, and then we can call it a day. So basically we just have that the error is equal to 1 over 2 times x squared. And this pretty much tells you that as you increase x, your error is going to increase significantly. So thank you very much, and I don't know if you have any questions.